Okay, hello everyone again. I would like to continue with our next speaker, which is Saptashva from the Center for Astrophysics and Cosmology. And please, Saptashva, share your slides and go ahead with your presentation.
Thank you for a nice introduction. Hopefully all of you are having a great day. And let me just begin. So I'll take you on a journey step by step to understand our universe a bit better. And I hope you already have a nice breakfast and you'll have some food for thoughts. And eventually you'll be able to burn some calories while you're thinking. And maybe you'll take some more books on the weekends. So let's begin. So I'll talk about how we can detect some very high energy radiation from the space and how it will help us to understand our universe better. We'll use a particular telescope called Cherenkov telescope head. I'll probably explain, or at least try to explain each term, and how we would like to study our universe with this telescope. So currently I'm a postdoctoral researcher in the Center for Astrophysics and Cosmology. We work in the Energični campus. So let's begin. So I always think it's best to get started with some basic introduction. And probably you already know that the visible light that we see, before we introduce gamma ray and detection of radiation, cosmic rays, I think it's better. We know that the visible light that we see represents a very small part of the electromagnetic spectrum. And you probably have seen some other applications of the electromagnetic spectrum. Like if you have a fractured leg like me from football, you have probably seen X-rays. And of course, in Europe, you have seen these radiators, which emit infrared radiation. And then probably if your mom bakes some cakes, probably you've seen microwaves. And if your grandpa had a radio, probably you've seen some radio. Anyway, so the idea is like from the right to left, if you go, the energy increases, the energy of the photons increases. And the other main concept is that the visible part of the spectrum is extremely small. So what we see is very small, but there are other methods to detect other part of the photons. Let's go. Okay, so now we understand that gamma rays are basically the high energy part of the electromagnetic spectrum. At this point, I think it's better if you know a bit more about cosmic rays. So what are cosmic rays? Cosmic rays are the high energy radiation that are coming from all directions and hitting the Earth every second. And the velocity of this high energy particles are extremely close to light. And whenever they hit atmosphere, they basically start to decay. And this is an artist impression from the image you see. Probably I'll show you a better simulation later. So we want to detect this kind of particles. Let's see some history, how it was detected initially. It was very interesting for me because the person who detected it, his name is Victor Hess. He went up on balloons carrying the detector several times. And these balloons were like as high up as like 6,000 kilometers. So like some Andes mountains or something like that. He was very brave, of course. And eventually he was awarded Nobel Prize, I don't know for his bravery or for the discovery, but let's say go with the discovery on 1936. The idea is like this opened a new door for us to study the universe. So now we have moved on over 100 years. We are now in 2021, so we don't need to be that brave. So we have balloons and satellites that go up by themselves and we just collect the data. So these are some representations. On the right, you see the Fermi-Lat satellite. And the left, there are some high-end equipped balloons in the Antarctica. So, okay, so now we probably know a bit about cosmic rays, that energetic radiation from the space, and how we can detect them. What are at least the methods? Now, specifically Cherenkov radiation. What is exactly Cherenkov radiation and how to understand this? Now, before I introduce the Cherenkov radiation, let me show you some simulation where these cosmic ray particles may originate and come from. So this is an artist's representation of a simulation from some, you can consider this as some violent events that are happening in some other galaxies. And the streamlined cosmic ray particles are coming as a jet, like a streamlined jet towards Earth. So these are some high energy events from some other galaxies, and this highly streamlined charged particles are coming towards Earth. They're getting close to Earth, but then something interesting happens when they start to interact with the atmosphere. Let's see what happens once they start to interact. Whenever they enter the atmosphere, they start to break down, as you can see here, from 1 to 2, from 2 to 4, 4 to 8, and this kind of breaking down we call in physics as disintegration of particles. Anyway, the idea is like charged particles from very high energy events coming from space, from other galaxies, from other astrophysical objects, enter atmosphere, breaks down. We want to detect these particles. When it breaks down, it creates the Cherenkov radiation. Why it creates the Cherenkov radiation, or how to understand this? So now let me take you back to high school. Probably you've learned that, okay, light is the fastest thing in the whole universe. It's partially right because there's a caveat, and the caveat is that it's fastest in the vacuum. It's not the fastest always. Any kind of material, there's a high probability there could be somebody else that's faster than light. And by somebody, I mean some high energy particles. I'll show you one example simulation. This is made by Fermilab. So you see on the top, the photons with the yellow wavy lines, and the down is basically the electron. Let's say we consider it as very, very high velocity electrons. When it's coming from the vacuum from the left, of course, the photon is leading ahead. It enters into a liquid chamber, the light slows down, but the high energy electrons, it doesn't slow down as much as the light. And eventually the electron takes over. What may happen if the electron carries enough energy, they may excite the molecules inside this liquid chamber or inside the material. You can think of air, glass, or something like that. Then whenever these molecules get excited, they start to emit photons. They start to emit light. What happens with those lights? There's another simulation. Again, once these lights are created, these photons are created, the initial particle, let's say, as I showed before, the electrons is still leading ahead of the photons. What it will create a conical shape of light form. And that is basically the Cherenkov radiation. We want to detect this light. You probably have seen some similar images. If you search in YouTube from sonic boom, exact similar thing happens, but instead of sound, happening now here in this case for lights. We want to detect this light. You may ask, okay, why we don't just directly detect the electrons or some other charged particles? The idea is like, as I have shown before, these particles will start to disintegrate, and they're very short-lived, like maybe a millionth or billionth of a second. But what it will leave behind is these traces of this Cherenkov light. They're usually blue, and if you search some nuclear reactors, you probably see in images in Google that these emit these blue lights. These are all Cherenkov radiation. We want to detect this Cherenkov radiation. How we can detect? I think at this point, probably I introduced you to the telescope. Where it is, how exactly it works. Let's dive in. Where it is. Can you take any guess from this image? So there are two positions, basically, 2 points in our Earth, northern and southern hemispheres. On the northern side is basically the Canary Islands, La Palma. On the southern part, we have the telescopes placed in the Atacama Desert in Chile. Now, the way we select the sites are basically on a moonless night. These are places with very dry weather, extremely clear skies, so perfect for night sky observation. Yes, so La Palma and Chile. So these are some simulations from the CTA telescope outreach team. They helped me to make this presentation. So this is from the La Palma Islands. This is a drone image. Very, very beautiful. Again, this is from Atacama Desert. As you can probably already understand that extremely less light pollution, very high elevation. So that means less air pollution and perfect for detecting this kind of cosmic rays. Not only CTA, but many other telescopes are also placed in this kind of environments. So this is an artist impression from the Atacama Desert. By the way, this height is about 4,000 meters. So it's already like the base of Everest base camp, very high. So the detector is not fully completed, but maybe after 2 years, maybe it will look like this. But we already have some mini telescopes. Before I show you the telescope or how it works, I think I should tell you that this is a huge collaboration consisting of about 32 countries and about more than 2,500 members, consisting of students, postdocs, researchers, professors, engineers, of course, because assembling this telescope takes a lot of engineering skill also, representing more than 200 institutions. And of course, Slovenia is a huge part of it. So 2017, Slovenia became a member of the CTA consortium, and our institute is the leading institute to study our universal city. And of course, particularly in our laboratory, members are actually directly involved with design and construction of the telescope. We are also involved in simulation, how the detector will perform. We are also involved in theoretical studies. Maybe we can also detect something you probably have heard in some documentary, something called dark matter. Probably it will be able to detect dark matter and many other stuffs. But this I'll explore later on the scientific targets. Also, Professor Gabriela Zaharias, she's my boss actually. She's also the co-coordinator of the Dark Matter Working Committee group. The main idea is that our laboratory is very highly involved with this huge collaboration. Okay, so now I show you some images taken by one of our PhD students. His name is Miha. So he went La Palma this summer. So this is a picture taken by him. So this is a telescope that are being assembled. Now you're probably wondering what kind of telescope is this and what are these hexagonal mirror kind of things. There's a zoomed in version. So this yellow hat guy, he is Miha, and others are basically members from Japan and Italy. Anyway, so of course, if you get involved with our laboratory, our research, probably you get to go to La Palma. I haven't been there, but I'm really excited to go there, of course, probably any normal human being would be, to see this kind of massive telescopes in person. Anyway, so how does it work? So what are these mirrors and how does it exactly work? Let's dive in. So this is again a large size telescope. Main idea are these hexagonal mirrors. How does this work? Let's zoom in to those hexagonal mirrors. The idea is whenever this blue flashes of light appears, of course, we can't see, as I have told you, because this is in the gamma ray region. So these blue flashes of light will be detected by these mirrors. These mirrors are basically some sort of sensors. They detect these blue lights, then the light basically reflects back to this region. What is there? There is basically, you can think of it as like a simple camera. It detects these blue flashes. And whenever it detects these blue flashes, this camera is connected with the data acquisition center. The signals will be passed through to the data acquisition center. And there's another arrow here. This is the people door. So this is just to tell you like how tall these telescopes are. And probably you have understood from the previous image that I showed from Miha. So this door is basically about 6 foot high. And this whole telescope is about 10 times taller. And this is a medium-sized telescope. The large-sized telescope is even taller. So the idea is these blue flashes of light, Cherenkov radiation, falls on the hexagonal mirrors, goes up to the picture taker, and then we basically get an idea. Okay, now let me talk about the science targets. What kind of stuffs we can possibly detect, what maybe we can understand. At this point, I think it's important to show you some images of why gamma ray is important. Why not other part? Maybe you can ask, why not radio or infrared? Why gamma rays? That's a great question. So this is a picture that I took from where I live. Basically, I live in a small village called Vipava. So this is the southern arm of the Milky Way, and Vipava is very clean, so it's possible to see Milky Ways in summer. And of course, if some of you are interested to see Milky Way, I probably should tell you in the northern hemisphere, it's probably July last week to August first week is the best time to see this southern arm, this dusty part of the Milky Way. And this is very important. If I look back to the northern part, which is looking towards Vargolia, another village, you see the brighter part of the arm. So this is the northern arm of the Milky Way. Now let me tell you that when we look towards south, this dusty part is looking towards exactly the galactic center, our Milky Way galactic center. But we can't actually see the galactic center from the northern hemisphere. It's visible from southern hemisphere. So if you ever visit for a conference or for study purpose to Chile or Australia, maybe you should take some break to go out of the city to see this southern part of the Milky Way. Now at this point, probably I should show you what are the other wavelengths can tell you. So this is the optical part, and this is the galactic core. These are the black parts. Black because basically the optical photons cannot reach us. The idea is like these optical photons have exact same energy that they get absorbed by the dust. But the scenario is completely different if we change the wavelength. There are many scientists working on radio, many scientists working on infrared detection. We are focusing on gamma rays. What essentially the message is, again, this was basically the second slide that I showed you. The visible part of the spectrum is very, very small. If we expand the photon wavelengths, and if we have some equipments to detect, we can unravel the mysteries of our universe in a very, very different way compared to visible lights. Now, of course, we are focusing on gamma rays. With gamma rays, we are trying to focus on the very high energetic events. Let's think of one of them. So this is a Crab nebula. So this is basically, you can think, somebody calls it also like a supernova remnant. It's basically what happens after a star bursts. It's the end of a star life cycle. This you can see at different wavelengths: ultraviolet, radio, infrared, and gamma rays. Now you see they look very different, and that's the main message. What we want to detect. Various scientists are involved in various parts of the detection. Of course, we can get the full message when we combine this data. Now, if you see the right part, basically the gamma ray image, you see the central object. I think I should tell you that this central object is something called pulsar. It's basically a rotating neutron star. And this is the high energy part. It basically emits the gamma ray. So with gamma ray, we can see the central objects. And with others, we can see other regions of this big starburst event. What are the other science targets? So since we are detecting high energy photons with CTA, we would be studying the most violent places in the universe. Maybe a supernova, like a starburst. Maybe the center of our galaxy, there's a black hole. Maybe some other star-forming regions where basically new stars are formed. Basically, let's say you can think of this as our galactic plane. Also, we should be able to know more what you already know about how these cosmic rays are formed, how they are coming towards our Earth, what are the energies. We'd be able to know more about other galaxies, what exactly happens to center of galaxies. Usually we believe that most of the galaxies in the center, they have black holes, just like our galaxies. And these black holes, if they're active, if you remember the simulation that I showed, the streamline particles that are coming from the center of galaxy, we can detect with CTA this kind of charged particles from the center of other galaxies. So basically, we can map the whole universe. And with northern and southern arrays, we can cover the whole sky. And of course, there are many other scientific targets, but since I'm running out of time, probably I should stop here and probably tell you more about our group. We have a very nice group, about 15 people in the Center for Astrophysics and Cosmology. So this is our group meeting picture from COVID time. And if you're interested, of course, not only about gamma rays and CTA, other research, very interesting research that's going on. So Tanya is here, so she works on supernova. So if you're interested in this kind of stuff, just scan the QR code or just go to the website to learn more about our group. Where we are based in the small town. Probably we have passed through this town many times. It's Izkušnja. So this is this blue building is our campus. Beautiful place. If you just go out, it's basically in the midst of nature. So just a coffee break would be very, very exotic compared to, let's say, some institutes in Vienna or in Tokyo, where I came from before. Very different. And of course, if you go out for lunch, if you stay late, go out for dinner in the laboratory, it's very, very beautiful and peaceful. Very different from where I was. So for me, it's very unique to study in this kind of environment. Anyway, so of course, you may be thinking that we are all scientists here. Probably we look like Einstein and probably talk among ourselves. Nobody understands us, but it's not the case. We also have a life away from research. So this is one of the events. I think Maria also showed this Gorica observatory. Apart from atmospheric research, we're also doing some laser measurement research. So some students, of course, our professors sometimes stay in these mountain huts. So if you consider to join our group, maybe you will be also get a chance to stay in these mountain huts and see very clear sky and see the Trieste Bay from those mountains. Anyway, so the idea is basically we have a life beyond research. And of course, the kind of work we do can also be related with high-end engineering stuff. And I should tell you, before coming here, I worked also as an artificial intelligence researcher in a company. So not only like very high-end theoretical simulation mathematics, but also this kind of skills are applicable in general company researches. About my life, I think I should tell you a bit. As I told you, I'm not like Einstein, so I have a cat, and we often go out in the mountains and recover. It's basically like one of the walks in the afternoon after I go back from laboratory. And I'm here for 1.5 years, and I still don't speak Slovene, so I thought the best way to become Slovene is to climb Triglav. So that's my attempt on this summer. Then, of course, I like photography. I go on many hiking trips, and this right images from a small village called Podkoren on the Kranjska Gora. Probably you already know if you're Slovene. Anyway, so we have a very, very interesting life apart from research. Of course, we love our research because the idea, I think we all think as scientists or astrophysicists, it's kind of for us, it's like a spiritual journey. We all know that we are made of stardust, and while studying universe in this kind of way is basically figuring out ourselves. And this is very exciting time. So our journey has just begun. So that's all from my side. I think you have enjoyed the talk. You already have some food for thought, so you burned some calories. And I can assure you that in the meantime, many cosmic rays have passed through your body. It's the truth of life, you know, it's government taxes and cosmic rays passing through your body. So you can't help. So that's
Thank you, Saptashva, for this very nice talk, amazing talk, especially for this personal touch as well. This is very exciting telescope that is being built at La Palma. So, which, as I understood, you have one of your colleagues, which is just there while
yes,
this
so he
volcano
was in the
has happened.
summer.
Can you tell us a bit more about this?
Of course, and I should probably, I forgot to mention. So one of our professors was there just a week back, just before the La Palma volcanic eruption happened. So he was being evacuated. So his name is Samo Stanec. He was there. So we are directly involved in assembling these telescopes. You probably have seen this kind of hexagonal mirror. So in the medium-sized telescope probably have about 90 meters, and big size, the large-scale telescopes, they have over 150 meters. So they are assembled piece by piece, and Miha is directly involved in calibrating these mirrors. So the idea is, maybe I can tell you a bit because now I have some time. So the idea is like once this blue light falls on this and it goes back, these arms are very light and this picture taker is very heavy. There's a big possibility to, while taking the picture, and this can also move. So we can point towards a certain direction of sky. To make the picture sharp, so this mirrors can move among themselves. And we need to calibrate to make this images sharp. So this is what Miha does with this laser experiments, how to make this images sharp, how to calibrate the instruments better. So he's directly involved in this kind of studies. And I think he already went 3 times. Yes, but I have never been. I am pushing someone to put me in there.
Do you have any like direct, I guess we can, Samo was also on the news talking about volcano eruption, which he saw with his own eyes. As you said, he has been evacuated. I'm now trying to find some pictures as well.
I actually asked him for pictures because that would have been nice, but I think he's very busy.
Yeah, this is quite exciting. I guess there hasn't been the volcano eruption at La Palma in the last 50 years or so, right?
Yes. Yes.
Amazing. Beyond this discussion on the volcano on La Palma, where these telescopes are being built, I would like to invite all the participants here, if they want to ask some question or another curiosity. If you have, please go ahead.
Yes, about the eruption. Is there a threat that it will destroy or So like destroy the telescope, or for you said that there are some new telescopes being built, so will they postpone that because of the eruption, or?
Yes, yes. So it's already postponed. I think so. Okay. So the best part that happened is that this volcano is actually on the opposite side of the island. But still, you can probably understand that there should be some way more volcanic dust and stuff. So I think for temporarily, I think for a month, I would assume at least for a month it would be stopped for sure.
Okay,
But
thank
also,
you.
I probably I should tell you that in the northern part, where in this La Palma, where this volcanic eruption happened, the telescopes that are already built. So this is an array, right? So there will be many telescopes, this hexagonal mirrors kind of thing. Some of them have already detected signals from the one that I showed you, this Crab Nebula, or the Crab Pulsar. They have already detected signals. The southern part is basically almost not at all in that working condition. So southern array will take more time, maybe 3 years. And of course, for the volcanic eruption, I think this is related with the detection of the cosmic rays. So that was the idea for detecting cosmic rays by Victor Hess. I think that's a very interesting point, since we were discussing about the volcanic eruption. So the idea was like, if we go up the atmosphere, the radiation will decrease because this volcanic eruption or the radiation from the factories or some stuffs would be decreasing. But once he put the detectors up, Victor Hess, he saw that this radiation is not decreasing as expected. It still maintains a level. And that was his idea, that it could be some radiation from outer space.
Okay, thank you very much.
Yeah, so here our colleague, so as you said, Samo Stanic has been also on the news. So here
Okay,
I found just one
sharing.
random news which is citing Professor Samo Stanic and his experience with the volcano at La Palma. Here, this is from yesterday. So yeah, quite interesting coincidence, I would say. Yeah. Any other questions from the other people we have joined here? Okay, otherwise I would we can stop here, and I would like to invite you for our next presentation that we have at 11:30. We will in the next presentation we will hear about how much plastic we are eating. So perhaps of the 4 presentations today, this one is the one that concerns ourselves maybe in the most direct way, I would say, because it's related to our health and everything else. So yes, please join me in 20 minutes or so here in the same Zoom. So I hope to see you all in a bit. And thank you for joining us. And especially thanks to Saptashwa, which about this great presentation about his work and the work of his Center for Astrophysics and Cosmology. Thank you all.
Yes.